In this section of chapter 10, we will talk about density and molar mass of a gas, and also we would discuss about Dalton's law of partial pressures. About density of gas, we all learned that PV equals to nRT, so PV equals to nRT, and then from here you can get, by simple algebra, you can get N over V equals to P by RT. Now, N over V, N stands for number of moles and V is in liter, so moles per liter. Now, if I multiply both sides by molecular weight, so M is the molecular weight, what we get molecular is gram per mole, so N has the unit of mole and capital M has gram per mole. So they cancel out. So Nm gives you gram. The bottom is liter, that's gram per liter, and that's the unit of density. So density is given by pressure times molar mass. In case of an atomic gas, it will be atomic weight. For molecular gas, it will be molecular weight. So basically we learned that density to be given by pressure times molecular or atomic weight, depending upon in what state the gas is, divided by RT. R has a fixed number 0.0821 liter atmosphere per degree Kelvin per mole. So let me write down the constant value, even though I gave that to you before, 0.0821 liter atmosphere Kelvin mole. We're now going to discuss about number 49. So 10.49. The question is, which gas is most dense at 1 atmospheric pressure and 298 Kelvin? So they gave three different formulas: CO2 gas, N2O, and the third one is Cl2. So they ask you to find out which of these gases would have the largest density. All of them are under 1 atmospheric pressure and 298 Kelvin. In order to think about this problem, let's first write down the density expression for the gas. It will be given by Pm over RT. When pressure is constant, temperature is constant for all these gases, R is already a constant. So basically, density is going to increase when molecular weight is increased. Density is going to be decreased when molecular weight is decreased. So let's now figure out these molecular weights. For carbon dioxide is 12 plus 32. Looking at that periodic table, we get these numbers. So that's 44. Nitrogen, each nitrogen is 14. Two of them will be 28. So 28 plus 16. And that gives 44. So that's also 44. Each Cl is 35.5, and you have two of them. 2 times 35.5, and that's 71. Since Cl2 has the largest molar mass or molecular weight, so Cl2 would have the highest density, and then carbon dioxide and N2 would have lower density, and both would have the same density value. So answer to this question is Cl2. They didn't ask you to calculate density value, so you just need to identify which of these gases had the highest density or most dense. So answer is Cl2 because it has the largest molecular weight out of all the three gases. Now let's go over our next problem, which would be number 53. So 10.53, I'd like to go over B. Okay, in this particular case, you need to calculate molar mass. So let's use those kind of symbols. M is for molar mass. So molar mass, you need to find out the value of molar mass. They're telling you that mass of the gas is 2.50 gram. That occupies 0.875 liter. And we know that density is given by mass over volume. Mass of the gas over volume. Now don't get confused between this mass and molar mass. Molar mass is gram per mole. That's basically molecular weight. And this mass, they already gave you 2.50 gram. 2.50 gram. And volume is 0.875 liter. 875 liter. And that gives you 2.86 gram per liter. So we already got the density value from the given information. Now pressure value is also given. So let's write down the value. 685 torr. So pressure is 685 torr. It's a good idea to write down the given information that we can think better about how to solve the problem. Temperature needs to be in Kelvin. They gave you 35 degrees centigrade. So 35 degrees centigrade plus 273. And that gives you 308 Kelvin. Okay, so these are the values that we got. Now we are going to use the formula D equals to PM over RT. And density value we already know, 2.86. 2.86. And 2.86 have the unit of gram per liter. So mass over volume. Pressure, they gave you the pressure unit. And the pressure has to be in atmosphere because it has to be consistent with the unit of R, which is 0.0821 liter atmosphere per degree Kelvin per mole. So let's change 685. So pressure is given by 685 torr, and we need to change it to atmosphere. 760 torr makes 1 atmosphere, and this gives you 0.901 atmosphere. 901 atmosphere. So now we can plug in all these numbers in right units, but before that we can solve for M. So let's first write down PM over RT, because we need to get the molar mass. Everything else is known. So M would be given by 2.86, so that's gram per liter times RT. So let's now use a different pen. R would be 0.0821 liter atmosphere Kelvin mole, that's R, and temperature is given, which is 308 Kelvin. 308 Kelvin. And then it would be divided by pressure. And pressure is given by 0.901 atmosphere. .901 atmosphere. Okay, so what I basically did is I used this expression and solved for M. So the first quantity, 2.86, is the density value. We already know. So density times R times T. The top number is dRT. So let me write down that. dRT on the top, and on the bottom you have P. So that gives you mass. Now this value is 80.27. 80.27. I think 80.3 would be fine because I see the top numbers have, these have 2 to 3 significant figures. Okay, this should have gram per mole. Our molecular weight is about 80 gram. Now we're going to do number 53A. So 10.53A. Question is calculate the density of NO2. So we need to get density of NO2. So the question mark is on D, density of NO2 at 0.970 atmospheric pressure. So pressure is 0.970 atmosphere. Temperature is 35 degrees centigrade. So I need to change it to Kelvin by adding 273. And that gives you 308 Kelvin. So that's 308 Kelvin. Now, density expression is D would be given by PM over RT. In order to calculate density, we also need to know molar mass or molecular weight. So molecular weight for NO2 would be given by mass of nitrogen, mass of N, plus mass of oxygen. Now we have 1 nitrogen and 2 oxygen, so it'd be 14 plus 32, and these numbers are coming from periodic table. So it's going to be 46 gram per mole. So now I'm going to plug in all these numbers. So D would be given by pressure is 0.970 atmosphere. Molar mass is 46 gram per mole. RT 0.0821 liter atmosphere per degree Kelvin per mole, and temperature would be given by 308 Kelvin. Now you can see some of these units would cancel out, and let me use a different color. Atmosphere would cancel out. Per mole on the top and per mole on the bottom would cancel out. Kelvin would cancel out with Kelvin. So now we have gram on the top, liter on the bottom. So that's the right unit, gram per liter, and the value is 1.76. So 1.76 gram per liter, and that's the answer to this question. Here we're going to discuss Dalton's law of partial pressures. So if you have a mixture of different gases, say for example I have mixture of hydrogen, nitrogen, and oxygen, so total pressure will be given by sum of individual pressures, and that's why we are using the term P1 plus P2 plus P3. And this is the expression given by Dalton's, and individual pressure of or pressure of a component in a mixture would be called partial pressure. Now, in these experiments, you can see that gas is collected over water. So what that means is water vapor is also mixed in the gas phase. So in order to know the pressure of a gas, you must subtract the vapor pressure of water from the total pressure. And that's how one gets the pressure due to the gas itself in the mixture of gas pressure and water vapor pressure. Now we're going to show you how to solve a problem on Dalton's law of partial pressures. So we'll have a mixture of different gases. This is number 65. So 10.65. Helium 0.765 mole of helium, 0.765 mole helium, 0.330 mole neon, that's also gas, and 0.110 mole argon, 0.110 mole argon. So that's the mixture of gases you have in 10-liter vessel. So volume is 10.00 liter. So that's the volume. Calculate the partial pressure for each of the gases in the mixture and calculate the total pressure of the mixture. So they're asking for partial pressure of each of these gases. I can show you how we can do that. Pressure of, say, helium times the volume is the total volume equals to nRT. So pressure due to helium would be given by nRT. We already know the number of moles of helium, which is 0.765 mole, and we know our value, and we also know the temperature. I think temperature is also given in this problem, 298 Kelvin. So temperature is 25 degrees centigrade. We add 273 to get 298 Kelvin. So that would give me RT. So it would be pressure due to helium would be given by applying pressure equals to nRT over V. So the total volume has to be given, and I think the question is asking for total volume of 10 liter. 10.00 liter. So make sure you do this math, plug in these values. R is 0.0821. Let me write down so that you can complete this problem. R is 0.0821 liter times atmosphere Kelvin mole. And temperature we already mentioned is 298 Kelvin. So make sure you plug in that and then get the partial pressure of due to helium. In the same way, you can calculate partial pressure for neon, partial pressure for argon. When you add up all the partial pressures, you get the total pressure. So let me write down here just the expression. Make sure you can finish this problem. Total pressure is given by partial pressure due to helium plus partial pressure due to neon plus partial pressure due to argon. So all these individual partial pressures will be added together and you're going to get total pressure.